Okay, so as we were saying, if the angular, so again, the picture is, imagine an object that's rotating in that direction, like so. That's what the velocity, angular velocity is telling you. And if the object is speeding up, the rotational rate is speeding up, that means the angular acceleration is pointing in the same direction. And if the object is rotating like that, and if it's slowing down, then the acceleration would point in the opposite direction. Okay, so that's what this is showing you. This diagram is showing you. All right. So what this now the next two slides. This is this uses cross products, and we won't use this often, but anyway, it's something that you need to, well, I need to show you at least once. Okay. The thing is, displacement, velocity, and acceleration are vectors. Okay, and vectors, of course, have direction associated with them. Okay, now we defined angular velocity for you guys, the direction of the angular velocity. So here was an object rotating like that, and the way you figured out the direction was you used your right hand, your fingers pointed in the direction of the rotation, and your thumb pointed in the direction of the velocity. Just like that. Angular displacement, delta theta is theta final minus theta initial. Okay, so the question is, what is the direction of the vector associated with this displacement? Okay, so again, you use your right hand, and if the object turned that way, so this point moved in that direction. Okay, the object turned that way, and your thumb was pointing in the direction of the displacement. And the greater your rotation, the greater the magnitude of this vector. What this vector is showing you, S, is the following. So as this object was rotating, so there was imagine that CD that was rotating. So this point on the CD that was that far away from the axis, this point moved that distance when the angular displacement was that. So that's what this is showing you. And this vector S, so the question, what this is, like I said again, this is the magnitude and direction of motion of this object. And again, these work only for small distances because this really is going on a circular path, and this will be if you consider small paths, the arc of the circle will be the same as a straight line. Anyway, so so what this formula shows you is the displacement of this point is the angular displacement crossed with the r vector. Similarly, as this object is rotating, there's the angular velocity. The velocity of the point on the CD at a distance r from the axis, that velocity is given by omega cross r. Okay. All right, I just wanted to introduce that. We won't be using these too much. Okay, so I just want you to be aware of it. Okay. Similarly, okay, so I'm going back to that CD example. As that object is rotating, and if it has angular acceleration, what does it mean by when you say it has angular acceleration? The CD is rotating faster and faster. Okay. So if it has angular acceleration, a point r distance from the axis on the CD, that'll have something called tangential acceleration. And that's what this is. Tangential acceleration is alpha cross r. Okay. And again, you guys understand, the further away you're from the axis of rotation, the greater your acceleration. And so that's what this formula is telling you. So this diagram, in this diagram, the CD has an angular acceleration in the opposite direction. Now let's make sure we understand this. So your CD could be rotating in this direction. Your velocity is in that direction, angular velocity. You can still have an angular acceleration in this direction. When will you have an angular acceleration in this direction? If you're slowing down. Or you could be rotating in this direction and speeding up, and your velocity and angular acceleration can point in the same direction. Okay. So anyway, you have multiple cases. So, but what this formula again is saying is, okay, so there's the CD that's rotating. If it has an angular acceleration, that it's rotating faster and faster, a point r distance away from the axis has a linear tangential acceleration given by that. Okay. All right, so let's pause now.